As a continuation of the previous scheduling algorithms, we are going to discuss about the next scheduling algorithm today, which is the priority scheduling algorithm. So priority scheduling algorithm, it is a third scheduling algorithm. So far we have discussed FCFS and the shortest job first. So in priority scheduling algorithm, each process is assigned in addition to its arrival time and the burst time. So far we have seen these two columns in our in every process. It has been having its own burst time, and the process ID is associated with the process, and also there is a arrival time for each and every process, the time at which it arrives in the ready queue. So these are the things we have seen before, but in addition to these two fields, that is its burst time and the arrival time, each process, it has another one term called as a priority. So that priority, the value of that priority, it tells us what is the importance of that process inside the as it arrives at the ready queue. So whether it can be given the CPU next or not. So that is decided based upon the priority of every process. So for example, we can either assign the numbers which are lower, that is, the lower the number, they may have the higher priority, or the higher the number, they may have the higher priority. So it depends upon the situation. We can change both. So both the non-preemptive and the preemptive cases are possible, as that of the SJF algorithm. In priority scheduling also, both preemptive and non-preemptive case is positive. So if suppose we are having processes which are that are present with the same priority, in that case we can remove the tie between those processes in the by looking at the order in which they have arrived in the ready queue. So this is how the priority scheduling it works. So these are the theoretical background based on the related to the priority scheduling. So now we can see the two different types of priority scheduling. One is non-preemptive and preemptive. So this is the non-preemptive case of priority scheduling. So as the name suggests, non-preemptive means once the process is allocated to the CPU, we will not take the process out forcefully out of the CPU. So until its burst time it's get completed, the process will be led to execute in the CPU itself, in the processor itself. So that is what is known as non-preemptive. So here they have given us 5 processes: P1, P2, P3, P4 and P5, and their associated arrival times. That is, this time indicates at which millisecond time the process has arrived in the ready queue, and then they have given us the burst time, and then the priority of each and every process is given. So as for this problem is taken into account, we have considered that the lower priority, lower numbers which is present here in the priority column, it is representing the highest priority. That is the importance of the lower number. The process which is having the lower number will be having the highest priority. So here P2 is having the highest priority first, and then comes P4, and then comes P1, and then P3, and then P5. So this is what I have mentioned previously. Sometimes they may give you the point that the higher the number, the higher the priority. At that time, the problem it entirely changes. So depending upon the situation, we have to act. So here it is a non-preemptive case, which is once the process is given to the CPU, until the completion of the burst time, it should not be taken out of the processor, right? So now, so we have seen that the process with the lowest priority, it should get the CPU first. So here the process P2 is having the lowest priority. Okay, but when you look into the arrival time of P2 is only 5. So only at the 5th millisecond, the process P2, it would have arrived at the ready queue. Until that, it will not be in the ready queue itself. So definitely at time 0, P2 has not yet arrived. So we are about to give only the process which has been arrived in the ready queue to the processor. So now at time 0, P1 has arrived. Even though P1 is having lower priority when compared to P2, since it has not, P2 has not arrived in the ready queue at time 0, we need to give the CPU only to P1. So now we are starting with P1 at time 0, and since it is a non-preemptive case, the burst time of P1 is 11. So starting from 0 for 11 units of time, P1 has to execute. We cannot take P1 outside, right? So by 11th millisecond, imagine by 11th millisecond, what are all the processes which would have come inside the ready queue? P1, it would have already, it is already present. Okay, so it is only executing for 11 millisecond. So P2, it would have arrived at time 5, and P3 only by 12. So definitely P3 would not have arrived. So P4 at time 2 it would have arrived, and P5 at time 9 it would have arrived. Okay, so P2, P4 and P5, these three processes, it would have arrived inside the ready queue at the end of 11th millisecond, right? So at that time we need to see what is the priority of these three processes. So among these three processes, which process is having the lowest priority? P2 is having the priority. P2 is having the priority as 0. So definitely I need to give the processor to P2. So P2 is being given at time 11. So the burst time of P2 is 28. So definitely it has to execute till 39, right? And then the remaining, so at 39th millisecond, definitely by 12th millisecond, P3 would have arrived. So now P3, P4 and P5, all these three will be in the ready queue, right? So at that time we need to see among these three which is having the highest priority. That is, the lower the number, higher the priority. So now P4 is having the highest priority. So P4 is being given to the CPU and its burst time is 10. So 39 plus 10, 49, right? So now the remaining P3 and P5. So among between these two processes, which is the having the highest priority? P3 is having the highest priority. So P3 is given to the CPU now. So P3 is executing for how many units of time? For 2 units of time. So from 49 to 51, P3 is getting executed. And now after that, the remaining process P5, so its burst time is 16. So it is starting its execution from 51 and it is ending by 67. So this is how the processes are getting executed in the non-preemptive priority scheduling case. And we, by seeing this Gantt chart, we plot the completion time and the turnaround time and the waiting time. So it is clearly given here. For P1 the completion time is 11, and for P2 the completion time is 39, and for P5 the completion time is 49, for P3 51, and for P5 67. So depending upon this, we may calculate the average waiting time and the average turnaround time. So now moving on to the priority scheduling preemptive case. So preemptive in the sense, what is preemptive? That is, once we give the process to the processor, and when a higher priority process it comes inside this, it is ready for the for its execution, definitely the process which is currently running the processor, it should be taken out of the CPU and that should be given to the again to the ready queue, and the process which is having highest importance, it should be given the hold of the CPU. That is called as preemptive, right? So the same way we are taking another one example for preemptive case. So here they have mentioned arrival time, priority and the burst time, and now we can see how it gets executed. So here as usual, by time 0 P1 it would have come inside the CPU, because only by seeing the arrival time, even though the priority is higher, we need to give only the arrived process. We will be able to give only the arrived process in the ready queue to the processor. So at time 0 P1 has come in, so P1 is put inside the CPU, so it will be executed for 1 millisecond of time. So after 1 millisecond we have to check whether any other process with higher priority has arrived or not. So at time 1, now the process P2 has arrived, right? So check the priority of that process. The currently running process having priority 3 and the newly coming process having priority 2. So obviously this priority P2 is having a higher priority than P1. So we may remove P1 from the processor and give P2 to the processor. So P2 has been given to the processor at 1 millisecond and now it is executing for up to 2. Okay. So now the burst time of 3, it would have been reduced to 2 because for 1 millisecond it has executed. Okay, now P2 has been given to the CPU and P2 is executing for another 1 millisecond, that is from 1 to 2, and at time 2 P3 would have arrived, but see the priority is 4, so definitely I can't take P2 out, so P2 has to execute another 1 unit of time, that is up to 3. Okay, now see at time 3 P4 has arrived. Now also the priority of P4 is 6, and but it is definitely it is lowest priority when compared to P2, so P2 will be again given the hold of the CPU and up to time 5, because at 4 none of the process has arrived, and at time 5 only P5 is arriving, and P5's priority is also, so up to 5 P2 is itself having the processor, and at time P5 P5 is also having priority 10, which is definitely it is higher than, the number is higher than P2, and P2 is having the highest priority now, right? So now what happens at this time, the burst time of P2 is 4, so definitely by from 1 to 5 4 units of time have been completed, so P2 would have completed its execution completely. Okay, now at time 5 all the process has arrived into the ready queue. Now every process, that is P2 is completed its execution, and P1 P3 P4 and P5, all the other 4 processes are present in the ready queue, right? Now based upon the priority we need to take the decision. Now the completely after all the process has arrived inside the ready queue, now the priority scheduling with preemptive case, it will work as that of the non-preemptive case. So what we have done in the non-preemptive case, we have just seen the priority of the process, and which one is having the lowest priority is given the option, is given the processor's hold, right? So now you see which process is having the highest priority, the lower the number, higher the priority. So 3 is having the highest priority, so remaining we are having 2 more milliseconds here, because for 1 millisecond P1 has executed. So now I am giving P1 to the CPU, and P1 is executing from 5 to 7, that is for remaining 2 milliseconds P1 is getting executed, right? And now after this the 3 P3 P4 and P5 processes are there. So among these 3 processes, P3 is having priority of 4, which is lesser, so P3 will get the hold of the CPU, so and this will be executing 6 milliseconds. The burst time of P3 is 6, so from 7 to 6 milliseconds, that is 13, up to 13 P3 will be executing, and then I'll be getting the hold of P4 to the CPU, and P4 will be entering, because when comparing 6 and 10, P6, that is P4 is having a highest priority, so P4 will be given to the CPU, and after that P5 will be given, right? So this is how we will be allocating the process to the processor in case of preemptive scheduling. So once all the process has been arrived into the CPU, arrived to the ready queue, we can shift the algorithm to non-preemptive case. That is non-preemptive in the sense, just we can look on to the priority and we can allocate, right? So P1's completion time is what? It is 7. We should not take as 1, we should take as 7. And P2's completion time is what? It is 5, right? This 5, and P3's completion time is 13, P4's completion time is 17, and P5's completion time is 19, and turnaround time minus the arrival time, it will give me the completion time. When we subtract the completion time from the arrival time, we'll be getting the turnaround time, and turnaround time minus the burst time will be getting the waiting time, right? So in this case of priority scheduling, imagine if the suppose higher priority processes are larger in number and the lower priority processes are too larger in number. In that case, the higher priority process will not let the lower priority process to get inside the CPU. So indefinitely the resources will be blocked from the lower priority process for a very long period of time. So this type of condition is called as starvation. Okay, so priority scheduling suffers from starvation. So this type of starvation can be avoided through aging process. So what is aging? So as that of aging happens in human, the same way the priority of each and every process is being increased for a constant period of time. After constant period of time, we increase the priority of the process by a particular amount. For example, after 2 seconds, we increase the priority of the process by 1 unit of time, or after 3 seconds by 2 unit of time. Likewise, we may increase the priority of the process that is waiting for a longer period of time in the system. So in order to avoid this starvation effect. So starvation happens in priority scheduling, and this can be overcome by using aging process. So this is one method to overcome the starvation problem. So with this, we are coming to the end of the priority scheduling, and the next scheduling algorithm we can see in the next class. Thank you.